For 60 years, every attempt to replace silicon has failed. Graphene, carbon nanotubes, and dozens of other materials that were supposed to be the future. None of them made it. But something just changed. For the first time, the semiconductor industry has quietly written a successor into its official roadmap. And if you look at that roadmap carefully, something remarkable happens. Silicon starts disappearing. Not from your laptop, but from the transistor itself. And the material taking its place is 3 atoms thick. Even stranger, a processor built from that material already exists. It already ran code, it performed a calculation, printed a result, and in that moment, the post-silicon era stopped being a theory. In this episode, we will look at the material that could replace silicon, the first working microchip built on it, and why the biggest prize here isn't smaller chips at all. Subscribe to the channel and let me explain. For more than 60 years, the entire computing industry has been built on a single material. Every smartphone, every laptop, every AI accelerator on the planet. And yet silicon was never supposed to make it this far. For decades, the industry was obsessed with one thing: making transistors smaller. Every new generation unlocked cheaper and more powerful computing, and that engine ran for half a century. But eventually, we ran into something we couldn't shrink away: physics. As transistors approached atomic dimensions, strange quantum effects started showing up. Quantum tunneling is the famous one. When electrons behave like waves, they can pass straight through barriers they were never supposed to cross. So current started leaking into places it was never meant to be. And at the same time, every new generation became far more expensive and far more difficult to manufacture. It looked like a dead end. And yet every single time, engineers found another trick. First, transistors stopped being flat. The channel was lifted up into a fin and the gate wrapped around 3 sides of it. That was FinFET, and it carried the industry through an entire decade. Then engineers figured out they could wrap the gate all the way around the channel, and that gave us gate-all-around. And honestly, the result is breathtaking. Those tiny horizontal bars inside a modern transistor are called nanosheets, and they are the pathways where electrons actually flow. They're stacked on top of each other, each only a few nanometers thick, engineered to switch faster while leaking less current. But it gets even crazier if you look underneath. In Intel's 18A, power no longer comes down through the crowded top of the chip. It's delivered from the back side of the wafer through what they call power via. So signal routing gets its own space, power routing gets its own space, and 2 of the hardest problems in modern chip making get solved in the same device. You would think there isn't much room left for new ideas. But the industry wasn't done. The next step is CFET, an attempt to build 2 transistors in the space of 1 by literally stacking one on top of the other. And after that comes even more stacking. Every generation bought silicon a little bit more time, but eventually every trick runs out. And that's exactly what makes imec's latest roadmap so interesting, because it projects the trajectory of Moore's Law all the way out to 2041. The next decade looks familiar, 2 nanometer class chips today. Then the industry moves toward A7 angstrom class technology around 2033, which will be a genuine milestone because that's where CFET is expected to make its commercial debut. 2 transistors, 1 footprint in mass production. But then something strange happens on that roadmap. Around 2041, silicon starts disappearing from the channel. Not from the wafer, not from your laptop, but from the tiny bar where the current actually flows. And the reason is almost poetic. After decades of shrinking transistors, if silicon can't be made any thinner, the only remaining option is a material that already is. Imagine taking a crystal and peeling it apart until only a single atomic layer remains. That's the promise of 2D semiconductors. And the leading candidate is a material called molybdenum disulfide. 1 layer of molybdenum atoms sandwiched between 2 layers of sulfur atoms. 3 atom layers in total, roughly 0.7 nanometers thick. Now, before you ask, this isn't some exotic unobtainium. Molybdenum is a standard industrial metal, mined at industrial scale for steel alloys. Sulfur is one of the most available elements we have, produced as a byproduct of oil refining. The scarcity problem that killed so many alternative materials isn't the problem here. The problem those materials had was something else. Take graphene, the most famous 2D material of all. Electrons move through it beautifully, and for a while it was supposed to replace silicon completely. But a transistor isn't a wire. A transistor has to switch off. And graphene has no band gap, which means you can never fully turn it off, which means it can't be a logic transistor. Molybdenum disulfide does have a band gap. It's a real semiconductor. That single difference is why the industry stopped chasing graphene and started chasing this instead. Carbon nanotubes had the opposite problem. Electrically, they're extraordinary, but a nanotube grows where it wants to grow, in the orientation it wants, with a mix of metallic and semiconducting tubes in the same batch, and a chip needs billions of identical devices in exactly the right places. Purity and placement killed it. And that's the pattern behind almost every failed silicon challenger. The physics was never the hard part. The manufacturing was. Keep that in mind because it comes back later in the story. And its thinness is the actual superpower here because it gives engineers the one thing they desperately want: control. The thinner the channel, the more completely the gate dominates the electrons inside it. Silicon nanosheets have to be kept under about 10 nanometers just to keep short channel effects in check, and going much thinner than that starts destroying the material's own mobility. A 2D semiconductor is under 1 nanometer by construction and keeps carrying current anyway. The semiconductor industry has spent decades trying to make silicon thin enough. This material starts thin. But here's the part most people get wrong. They assume this is about making transistors smaller. It isn't. In imec's own framing, 2D materials enter the roadmap for power, not for density. When the channel is only a few atoms thick, the gate gains extraordinary control over the electrons flowing through it. Better control means you need less voltage to flip the switch. And in semiconductors, voltage is everything because the energy burned in a switching transistor scales with the square of it. Drop the supply voltage by a third, and you don't save a third of the energy. You save more than half. That's why lab devices built on this material are being demonstrated at operating voltages of 0.2 and 0.3 volts, with switching behavior that silicon physically cannot reach. And that's why this story is way bigger than transistor scaling. Right now, AI is pushing the industry straight into an energy crisis. Data centers consumed around 415 terawatt hours of electricity in 2024, roughly 1.5% of the world's electricity, and the International Energy Agency expects that to more than double to around 945 terawatt hours by 2030. That's more electricity than Japan uses today. The industry doesn't just need more computing anymore, it needs more computing per watt. And a transistor that switches at a third of the voltage is one of the very few things that changes that equation at the root. But a roadmap is just a plan. A slide is just a slide. The obvious question, the one researchers have been unable to answer for more than a decade, is whether you can actually build a computer out of this stuff. Not one transistor, not 100. A real processor that executes real instructions. And now, finally, we have an answer. In 2025, a team at Fudan University in Shanghai published a chip called RV32-WUJI. It contains 5,900 transistors, and every one of them uses a molybdenum disulfide channel about 3 atoms thick. It implements the RV32I instruction set, the base 32-bit integer instruction set of open source RISC-V built from a standard cell library of 25 different logic units. And it works. It fetched instructions, decoded them, and ran them. The demonstration calculation the team published was almost a wink at the audience. 1946 plus 25 equals 1971, the year Intel shipped the world's first commercial microprocessor. Then 1971 plus 53 equals 2025. Now, 5,900 transistors sounds tiny. And at first glance, it's easy to be disappointed because NVIDIA's Rubin GPU packs 336 billion transistors into a single package. But that comparison is the wrong one. Intel's 4004, the processor that started the entire industry, had 2,300 transistors. This chip has more than twice that. And unlike the 4004, whose features were measured in micrometers, the active material here is 3 atoms thick. It's slow, running at around 1 kilohertz, which is roughly a millionth of the clock speed of the phone in your hand. But speed was never the point of this experiment. Existence was. And the number that should actually make you pay attention isn't the transistor count. It's the yield. The Fudan team reported around 99.9% of individual transistors working and 99.77% of inverters working. When your semiconductor is only a few atoms thick, almost everything can go wrong. A single missing sulfur atom is a defect. A wrinkle in the film is a defect. Getting one atomically thin transistor to switch is difficult. Getting thousands of them to work together consistently across a chip is an entirely different kind of problem, and they solved it well enough that the circuit runs. And there's a detail in that project that tells you how early this all is. When you design a silicon chip, you don't place transistors by hand. You pull from a standard cell library thousands of pre-characterized building blocks backed by decades of design automation software that knows exactly how those cells behave. For a 2D processor, none of that exists. So the team had to build their own library from scratch, 25 different logic units, and characterize every one of them before a single instruction could be executed. That's not just a new material. That's rebuilding the entire design stack above it. And this is no longer a single isolated result, which is what makes it feel like a turning point rather than a stunt. At Penn State, a team built a working computer using more than 2,000 2D transistors on a single chip, and they did something the Fudan chip didn't. They used 2 different 2D materials together, molybdenum disulfide for the N-type devices and tungsten diselenide for the P-type devices, to build real complementary logic. Then in June 2026, researchers from Nanjing University, Suzhou Laboratory, and Huawei went further and published a 4-bit parallel processor with more than 1,400 molybdenum disulfide transistors, complete with an instruction decoder, a register file, and an arithmetic logic unit at a density of over 9,300 transistors per square millimeter. In roughly a year, the field went from 1-bit serial curiosities to processors with real architecture inside them. So the question has changed. For years it was, can these atomically thin transistors work at all? Now it's, can this be manufactured? Because that is precisely where every silicon challenger before it died. The device existed, the process didn't, and that may finally be starting to change. In June 2026, imec, ASML, and TSMC presented something the field had been waiting for. Not a lab device on a fragment of material, but 2 D-material transistors integrated on standard 300mm wafers patterned with single-exposure EUV lithography at a contacted poly pitch of 50 nanometers with channel lengths down to 28 nanometers. Molybdenum disulfide for the N-type devices, tungsten disulfide, and tungsten diselenide for the P-type ones, with tungsten-filled contact trenches only 19 nanometers long. And 94% of those transistors switched properly. Read that again. Pitch scaling at industrial dimensions, on industrial wafers, in an industrial tool set, with the world's 3 most important names in advanced manufacturing standing behind it. That's not a physics demonstration anymore, that's process development. But nobody at imec is claiming this is finished. And it's worth being precise about what still stands in the way because they've been unusually clear about it. There are three problems. The first is channel quality. Defectivity in the grown film is still the main thing holding device performance back. The second is contact resistance, and this one is nastier than it sounds. To get current into a transistor, you have to physically connect metal to the semiconductor. With silicon, you have a three-dimensional volume to make that contact into. With a 2D material, you're trying to inject current into a sheet less than a nanometer thick through a contact only a few tens of nanometers long, and every ohm of resistance you add there eats directly into the performance the thin channel just bought you. The third is modeling. You cannot design a chip on a device you cannot simulate accurately, and the compact models for these transistors with realistic process assumptions baked in are still being built. None of those three is a physics wall. All three are the kind of grinding, unglamorous engineering that takes a decade. But there's a layer underneath all of that which almost nobody talks about, and it's the hardest one. Before you can pattern a 2D transistor, somebody has to grow the material. And that turns out to be the real bottleneck between a lab and a fab. Think about the head start silicon has. 60 years of learning how to pull enormous, nearly perfect single crystals, slice them into mirror flat wafers, and build billions of devices on top. Molybdenum disulfide isn't a single element you can melt and pull. It's a compound. Every molybdenum atom and every sulfur atom has to land in exactly the right place, in exactly the right ratio, across an entire 300 millimeter wafer, in a film that is 1 atom thick. Imagine painting a football field with a brush 1 atom wide and not being allowed a single stray stroke. That's the level of precision. And then comes the real enemy: grain boundaries. As the film grows, tiny crystals nucleate independently in different orientations. They expand outward. Eventually, they collide. And where they meet, the atomic lattice doesn't line up. Think of a frozen lake, where ice forms in patches and cracks appear along the seams. In a semiconductor, those seams become scattering sites, leakage paths, and device-to-device variation. Silicon spent decades learning to eliminate defects like these. 2D materials are starting that clock now. And this is exactly where promising technologies have failed before. Not because the transistor didn't work, but because the manufacturing never did. One of the companies attacking this problem directly is C-Dimension, a spin-out from MIT. Their focus isn't the transistor at all, it's the film. And their approach is elegant. You flow gases containing molybdenum and sulfur across a wafer. The atoms react on the surface, and a crystal a few atoms thick slowly assembles itself. The catch is temperature. Conventional growth of these materials wants somewhere near 1000 degrees Celsius, which is hot enough to destroy anything already built on the wafer underneath. C-Dimension grows molybdenum disulfide at around 200 degrees and tungsten diselenide at around 450, and they supply it on wafers up to 300 millimeters. And that low temperature is not a convenience, it's the whole story, because it opens a door that silicon can never open. If you can build transistors at 200 degrees, you can build them on top of finished circuits without cooking them. And that means replacing silicon might not even be the interesting outcome. Building on top of it might be. This is where we touch the idea of true monolithic 3D computing. You build a layer of silicon transistors, then you grow a layer of 2D transistors directly on top of them. Then another, like constructing a skyscraper where every floor is a complete logic layer. And that idea sits at the end of a very clear progression, which is worth laying out. Because 3 different technologies are all solving exactly the same problem from 3 different directions. The first is CFET, stacking 2 transistors on top of each other. That's adding a second floor to the transistor. The second is stacked logic through hybrid bonding, which is where Huawei's work has been pointing with what they've been calling logic folding under their Tau scaling framework. There, you manufacture separate logic layers and then bond them together with millions of tiny vertical connections. That's adding another floor to the chip. And monolithic 3D goes one step further than both. Instead of building two dies and joining them, you build the layers directly on top of each other from the beginning, inside a single chip. No bonding interface, no alignment budget between wafers, just one continuous structure. If CFET adds a floor to the transistor and hybrid bonding adds a floor to the chip, monolithic 3D builds the entire tower, with shorter connections and far less energy wasted shoving data sideways. And that last part matters more than the density does, because in a modern chip, moving data burns more energy than computing with it. That's why the biggest names in the industry are watching this so closely. Not because this material is better than silicon in every way, it isn't, but because it's a path forward when traditional scaling finally runs out of road. And this race is bigger than a single material, which is something the headlines usually miss. Molybdenum disulfide gets the attention, but it isn't running alone. Research labs, including imec, are working with tungsten disulfide, tungsten diselenide, molybdenum telluride, and a whole family of what chemists call transition metal dechalcogenides. Think of them as siblings. Same atomic architecture, slightly different electrical personalities. Some are better at carrying electrons, others are better at carrying positive charge. And modern logic needs both in balance on the same chip. That's why the Penn State computer used two different 2D materials and why imec's 300mm demonstration used three. So the future here probably doesn't belong to one material. It belongs to a family of them working together, chosen layer by layer for the job each one does best. Which brings us to the honest part of the story, where this actually shows up first and when. If you're expecting the CPU in your next laptop to be atomically thin, that's not how this goes. New device technologies almost never arrive at the top of the market. They earn their way up. The first commercial applications for 2D materials are far more likely to be things like radio frequency switches for future 6G front ends, sensors, MEMS devices, and specialized back-end of line components sitting above conventional logic. imec's own roadmap reflects this exactly, targeting 2D devices first in peripheral applications at A7, with the high-performance version, a full 2D CFET, as the longer-term goal further out. And those early applications are not a consolation prize. They're the proving ground. They don't need billions of flawless transistors, so they can tolerate the defect densities the material has today while the process matures. That is how almost every new semiconductor technology has entered the market. First in a niche where the requirements are survivable. Then, years later, at the center of mainstream computing. It may sound slow, and it is slow. From the moment a new transistor concept is first imagined to the moment it ships inside a consumer product, you are looking at something close to 2 decades. Silicon photonics spent years in what engineers call the valley of death. So did EUV lithography, which was written off repeatedly as physically impractical before it became the single most important machine in the industry. High-K metal gates, strained silicon, FinFET, every one of them looked immature and unmanufacturable right up until the moment they weren't. So step back and look at what has actually happened in the last few years. A material that was a physics department curiosity now has an entry on the industry's official long-range roadmap. It has processors, plural, that execute real instructions. It has yields above 99% at the device level. It has 300mm integration with EUV patterning at 50 nanometer pitch, developed jointly by the most important lithography company and the most important foundry on Earth. And it has a growth process cool enough to build logic on top of finished logic. None of those things were true 5 years ago. That's not a replacement for silicon. Not yet. And maybe not ever in the way people imagine. But it is the first time in 60 years that the industry has an answer to the question of what comes after, and has started writing that answer down in ink instead of speculation. The real question is what we do with it. If the industry gets a transistor that computes at a fraction of today's energy, does that give us AI systems that stop consuming the output of power plants? Or do we simply build models 100 times larger and end up burning exactly as much as before? Because historically, every efficiency gain in computing has been spent immediately on more computing. I'd like to know where you land on that. Drop your take in the comment section below, and if you enjoyed this episode, share it with someone who still believes silicon is forever, and subscribe to the channel.